Good morning. This is the 12th lecture in advanced computer algebra, and we are in the middle of discussing polynomial factorization. We have already discussed polynomial factorization for the case when the coefficient field is a finite field. This is what we did last time here. And we saw that this could be solved with the Cantor-Zassenhaus, and it can be solved quite efficiently. Cantor-Zassenhaus is not the most efficient algorithm that we know, but it's a reasonably efficient one, and it's efficient both in theory and in practice, and it's the default algorithm that is used in most of the computer algebra systems today for factoring polynomials over a finite field. And factoring polynomials over a finite field is sometimes a problem that you really need, but it's mostly interesting because it's a building block of polynomial factorization algorithms for other ground fields, in particular for the rational numbers, and maybe that's a problem that you may find more natural or more important than this one. And we will now work towards a factorization algorithm for polynomials over the rationals, but we don't go there directly. We'll first go to an analogous situation here that I think is worth to explain before. Not so much because it's interesting in its own right, but more because this is easier to understand, and when you have this in mind, then it's easier to see what we will later discuss when we move to this area here. So this here is also not explicitly included in the book of von Sogarten and Gerhard, but I'm including it here mostly as a preparation for, or as a motivation for the techniques that I will later discuss here and there. So what is this? This is polynomial factorization over the field of Laurent series in a one variable t. You know, a formal Laurent series is like a power series, except that a Laurent series may have also monomials with negative exponents, as long as they are just finitely many. So you can say it's a power series where the starting index of the infinite sum may be any integer, but then it goes only up, and it can't be going arbitrarily far into the negative exponents. This is a formal power series. You know that they form a field, and this field is actually the fraction field of the ring of formal power series. And a formal power series and also a formal Laurent series is an infinite object, so we cannot expect such an object to be the input of an algorithm. We will assume that the input of the algorithm has a polynomial, is a polynomial in X, whose coefficients are polynomials in T. And of course, a polynomial is in particular a power series, and then also in particular a Laurent series. So why don't we just say polynomials here? Because the factors may have infinite series in its coefficients, and to compute these factors will mean to compute the coefficients of these coefficients up to any desired exponent. So there may be infinite series in the coefficients of the factors, of course not in the input, but in the coefficients of the factors. And we want to be able to compute as many of them as we want. And this is a step towards rational factorization, which in this case means factorization of polynomials over a rational function field in T, which then will translate into, or will motivate the techniques that we can use for factorization of polynomials over the rational numbers. Okay, so let's go for it. Here's the summary. The goal is that we assume that the K here is a field for which we can already solve the factorization problem. So what we do here is a problem reduction for ultimately the field of rational functions, and as an intermediate step the field of Laurent series as coefficients. We want to factor polynomials over this, assuming we can factor polynomials over this. Okay, and the reason why I'm introducing this as an additional section in our story of factorization is that I can illustrate here more easily what is going on because I can draw pictures. It's not so easy in the integer case, and more easy here where I have two variables, and if I'm given a polynomial, then I can ask for the roots of this polynomial. It's a polynomial in x, so the roots, well, what will be the roots here? Finding roots is more or less the same as finding factors, but I can view this also in such a way that the t is a variable and the x is a function of t. And then if I view the m as a bivariate polynomial, then I get a curve in the plane. So here is t and there is x. And so this is an algebraic curve. It's determined as the roots, the set of all roots of the polynomial. So the set of all points t comma x, such that when I plug x and t into this bivariate polynomial, I get 0. So it's not just one root, it's an entire curve of roots. And such a curve can have special features. For example, there could be pole places. So here there is a t, for which if you view this as a function, you have a pole. So the x goes to infinity when t goes to this blue point. That's one thing that such curves can have. And another thing is that they don't form functions because they can turn around. They could have such places here where the tangent is vertical. So this is called a branch point because at this area the curve doesn't describe a function. It does describe a function anywhere else, just at least locally. But here it's a branch point. It's called a branch point because the curve branches into an upper part and a lower part in this picture. And all the other points are ordinary points, and I already said that the ordinary points are so that if you look locally at an ordinary point, for example here, so this is the ordinary point, but this is the curve in the neighborhood of this ordinary point, and in this neighborhood the curve can be viewed as the graph of a function that maps t to x. Okay, so this is the setting. Now let's translate this into this picture into words. So if what does it mean to be a pole place? A pole place is, if you assume that the m is monic, then a pole place will be where a denominator of the coefficients of m vanishes. So let me maybe write this down a bit more explicitly. So the m will be m0 of t plus m1 tx plus md minus 1 tx to the d minus 1 plus x to the d. And these m's, they are all in Ct, so they are rational functions. And that's one way of viewing it, but you can also say you clear the denominator and you say or the m is m0t plus plus md of t x to the d, where these coefficients now are polynomials, but with no content. GCD of m0 and md is 1 in Ct. Okay, and of course this is not the zero polynomial. And in this formulation, you see that there are interesting things going on when the t runs through the complex numbers and hits a root of this polynomial. Because when it hits a root of this polynomial, then the degree of the m at this particular t will drop, because then this term will disappear, and then it depends on what is below. And this is what you observe here at a pole place, because always at every other point, so the m here will have a certain degree in x, and that means for a specific choice of t, you will have a certain number of roots that is determined by the degree of the polynomial in x. So here you have 3 roots, 1, 2, 3. Now here you also have 3 roots, 1, and the other 2 are complex, so we don't see them. But here at the pole place, there's really a root missing. So there are 2 complex roots that we don't see because they are complex, but that's all. The other root is gone, and that's because the leading coefficient of this m, if you write it so that the that the coefficients are polynomial, the leading coefficient vanishes. So on the other hand, if you if you prefer to have a monic polynomial, then that means this leading coefficient will be the denominator in the denominator of all the other coefficients. And so this is where the pole places, you can recognize them as the roots of the denominators of the rational coefficients of the monic m. And the branch places are also easy to recognize because they are the ones where the curve has a vertical tangent. And a vertical tangent means that if you turn this picture around, flip it by 90 degrees and view this as a function of x that maps x to t. So if you maybe don't rotate it, maybe flip it at the diagonal, so that it becomes a function, and then you see this vertical tangent becomes a horizontal tangent, and that means that you have a double root, or at least a multiple root of this function, or a root of the derivative, but also a root of the function because it's on the curve. So it's a common root of the function and its derivative, and you know hopefully from computer algebra 1 that you can get the common roots of 2 polynomials by considering the resultant. The resultant will be a rational function in the remaining variables. So x is eliminated. You can eliminate with Gröbner basis also if you prefer this. It gives the same answer. But the point is there is a certain polynomial or a rational function so that all the branch places are among the roots of this rational function. And all these other points are ordinary places. So ordinary places are the ordinary case, the usual case, and the pole places are just very few, and the branch places are also just very few, and we will avoid them because they cause trouble, and we look at what happens at an ordinary place. If you understand what happens there, then that will be enough for our purpose. Of course, we understand we can also build up a theory that explains what is happening at these places, but that should not be our business. Okay, so t is an ordinary point. So if and only if replacing t by this tau in m gives a square-free polynomial in the remaining variable x that has the same degree. So the same degree means it's not a pole place, and square-free means that if the m was square-free before, as I'm assuming here, then I'm not hitting a branch place, because at a branch place plugging such a branch place into t gives me a polynomial where I have here a double root. So this would be a double root, and this would be another root. So there will still be 3 roots, unlike at the pole place, still be 3 roots, but one of them would be doubled, and that's not what we want. We want to keep the things square-free. Okay, so here's a more precise example. A polynomial that is factored. And for the polynomial to be factored, that translates into the geometry that the curve has more components. So here is one component. This is a parabola, but with x is exchanged. And the other one is a hyperbola, which in the real looks like it has 2 components, but actually this is just one component if you view it in the complex plane. So the components of the curve correspond to the factors of the polynomials. And now look what happens if I evaluate this polynomial and substitute 0 for t. Now, if you substitute 0 for t, then that means you're looking only at the vertical axis, and you get a polynomial that has 3 roots, here, here, and here. And I want to turn these roots, the knowledge about these roots, into a knowledge about the roots of M. Okay, so this means there is a curve which I now paint in gray, because I assume I don't really know it. But in the neighborhood of these roots of this polynomial, this curve can be described locally as a function that maps t to m. So it will map 0 on this axis to the roots 0, 1, and -1. But in the neighborhood, we can get some information about these curves. And that will be useful because these functions here, if I'm viewing them as if I expand them as power series, then these power series would be power series roots of m. Okay, and that's what we want. We want to factor the polynomial m over the power series. Now, actually over the Laurent series, but power series will be enough if we choose here an ordinary point. And so finding the roots of m is the same as factoring the m, and finding the roots of m is the same as turning a root of this specialized m at t equals 0 into a power series expansion of the curve around this point. So here the roots are 0, 1, and -1, but the power series expansions, well, they contain more information. The question is now, how can I go from these roots of this m0 to the power series expansions that give rise to the roots of m. And you know this already from your original or from your very early calculus education. This is called the implicit function theorem. You may have seen this in the context of real analysis, but it works also formally. And here's the statement. If you have a tau that is in the ground field, and that is such that it's an ordinary point, so it has the properties that m evaluated for t equals tau is square free and doesn't have a degree drop, then every root of this evaluated polynomial can be uniquely extended to a root of the bivariate polynomial in the power series ring. That's what the implicit function theorem says. And it's not just an existence theorem. The theorem is constructive. If you look at the proof of the theorem, then it tells you how to construct the terms of this power series expansion if you're given the tau and the initial root of the specialized polynomial. So let me remind you how this works. Let's consider the case where tau and xi is 0. Just for simplicity, if you have any other points and you make a change of variables, do a change of variables, and you will be in this situation. So if the tau is 0 and the xi is 0, and you write the m like this, then you can proceed as follows. First, you know that the m0 at 0 is 0. Well, that's because xi is supposed to be a root of the specialized polynomial, and this here is the specialized polynomial. So this here will vanish at t equals 0. And this here will not vanish at t equals 0 because we are not at a branch place, so there's no double root. So we have these two assumptions. And now suppose, so this is an induction argument. You compute one term after the other, and you see the power series here starts with 0 times t to the 0. That's because xi is 0. So it starts with t. And suppose we have already computed the first n terms. That means we have a polynomial which is such that if I plug it into the m, I get 0, but not exactly. I get actually a polynomial whose smallest exponent of t is n, n plus 1. So that if I take this polynomial here, mod t to the n plus 1, then I get 0. And then the question is, having this, how do I get the next term? Yeah, you just make an ansatz for the undetermined coefficient and see what will happen if you plug an additional monomial here with this unknown a n plus 1 and the known part that you have already computed into this polynomial. What you want is this equation, but with the next highest power of t. So, okay, you will get m1 of 0, which is this one, times a n plus 1, plus things that are independent of a n plus 1. If yeah, so if maybe I should have written this here. This is only equal mod t to the n plus 2. So the a n plus 1 will also appear in the higher order coefficients. Yeah, so what is written here is the coefficient of this expression, the coefficient of this monomial in this expression. This is what we want to turn 0 so that the equality holds true mod t to the n plus 2. Okay, and then there's a unique choice so this is an equation that you can solve, because here there's stuff that doesn't contain the unknown variables, so it depends only on the a's that you already have, and it's maybe a complicated expression that I didn't write out here, but this one is non-zero here by assumption, and you want this to be 0, so you're just solving this for a n plus 1, and there's exactly one choice for the next term, and then you keep going. Okay. So this is about the choice of, this is about the construction in the implicit function theorem. Now how to choose the tau. Remember, the tau was the point where we do the expansion. In the example it was 0, but what we need in order to apply the implicit function theorem is that the tau is an ordinary point. We have seen before that almost every point is an ordinary point, and every ordinary point matters. So if k is an infinite field, for example the complex numbers, then almost every choice is okay. You just have to avoid the pole points and the branch points, and we have seen that there are only finitely many of them. And another question is, when you then plug in the tau for the t and get a univariate polynomial that doesn't have a degree drop and that doesn't have multiple roots, then you still have to find the initial term of the power series expansion, and that's a root of this m, for t equals tau. And it may be that this is an irreducible polynomial. So what do you do if there's no root? Now we can assume that we have the assumption that we can factor over k, polynomials over k. So you can take this polynomial and factor it, and take an irreducible factor q of it, and then you extend the field by a formal root of this polynomial. So this polynomial may not be irreducible, but this one is, and you can find it by assumption. So you go to the extension field kx mod some irreducible factor of it, and then this polynomial here, when viewed as a polynomial over this extended field, this will have a root, because this x here will be a root of this polynomial by the choice of q. So that means if you don't have a root, then by the assumption that you can factor, you can extend your field, and then you will have a root. Okay, so in summary, if the tau is not too bad, and we saw that only finitely many taus are bad, then we can find a field extension of L so that the M has a root in this power series ring, which in general is in t minus tau, and over the extended field. And using the idea in the proof of the implicit function theorem, we can get as many terms as we like of this power series. And this settles this part here. So this is really the summary is this is done by the implicit function theorem. It's really a matter of root finding, and root finding is very closely related to factorization. And now let's turn to rational factorization. How does this one help us here? This is the question. So how if we have a polynomial in two variables and we view it as a polynomial in x over the rational function field in t, and we have now a power series root, how does this knowledge help us to find a factor of m in this field? Okay, so we could just make an ansatz. That's one possibility. So let's say we have computed with the implicit function theorem lots of terms of the power series expansion of some root, and what we want to do is, or the idea is now to take this as input and forget about the m for a moment and just search for a polynomial that is likely to also have these power series as a root. And what do I mean by being likely to have this as a root? Now, this is really what I'm giving is just a polynomial, but I view this polynomial as the initial segment of a power series that extends indefinitely to the right, but I don't know how it extends to the right because I'm just given a finite amount of data. So I don't want to have a polynomial p that exactly it has this one as a root. That would be easy. I would just take x minus this polynomial. It would have this root, but it would have coefficients that have high degree in t. What I want rather is something that has low degree in t compared to n. And that means in reverse that when I apply this technique, then I would have to ensure that the n is large compared to the degree of p with respect to t, and the degree of p will be related to the degree of t in m, and m is the input. Okay, so the goal is to find a polynomial that has low degrees and it has this polynomial. Yeah, I should say it has a power series solution that also starts like this. This is the way of putting it. And so this means that if I plug this into the polynomial, then I should not get exactly 0, I just should get 0 mod t to the n, like in the proof of the implicit function theorem. Okay, and once we have such a p, then we can compute the GCD of this p and m, and this will be a factor of m in the polynomial ring over the rational function field. Of course, this may be a trivial result. So it might be that the p is a multiple of m and then the GCD is just m. This is something we can avoid because we can choose the p and the shape of the p in this computation and maybe make sure that the p has a lower degree in x than the m does. Then the p cannot be a multiple of m. But there is still another way how this can break. The GCD could be 1. And this can then mean two things. Either there is no such p, or I haven't taken enough accuracy here, and I would have to repeat with larger n. Okay, but how do I find a p in the first place, or prove that no p exists? You can do this with linear algebra. So a p will be a polynomial. The p is a polynomial in t and x with coefficients that we don't know and want to determine. And as I said before here, the degree in x is chosen one less, or at most up to one less than the degree of m. And since this p is ultimately going to be a factor of m, the m is a polynomial not only in x but also in t, you can also bound the degree in t of the p. It can't be larger than the degree of m with respect to t. Okay, so let's say this is r. Okay, now I plug for x into x. I plug this truncated power series solution of m, and then I get a very long polynomial in t that has some coefficients that are linear combinations of the unknown coefficients pij, which I don't know and want to compute. And the a's here, they are known, and they will also appear there. And then what I want to have is that this resulting expression will be zero for the first so and so many terms with respect to t, and then I just force them to zero. So I equate the coefficient, the first n coefficients to zero, not more because I don't have more accuracy here. But for those ones, it's necessary in order for the p to have the a as a root, or a power series that starts like a as a root. And this gives a linear system for the unknown coefficients pij. And typically, the system will have more equations than variables. It will have here n plus 1 equations, and it will have d times r plus 1 variables. That's the number of undetermined coefficients. And I can ensure that the n is larger than the number of variables, and so I get an overdetermined system, and then I don't expect to have a root. Okay. And this result may be inconclusive. What does this mean? So there are two possibilities. Either you find a solution. Actually, there are three possibilities. So one possibility is that the system has no solution, no non-zero solution. Then you know that p is that there's no such p, and then the m is irreducible. Because if it had a root, then if the m were not irreducible, then this root would belong to one of the irreducible factors, and the irreducible factors would be smaller than m. And I'm searching for a polynomial that is smaller than m, and but I didn't find any. But it would have to appear, the minimal polynomial of this root would have to appear among the solution set of this linear system. And if it doesn't, because the solution set is empty, then that means there is no smaller factor. And that implies that m is irreducible. So that's not inconclusive. That's something where you can be sure that you have solved the problem. The other case where you can be sure that you solved the problem is when you find a solution, and it's a p for which the GCD is not 1, because then you have found the factor of m, and then you're also happy. But it could be that maybe the linear system has more than one solution, and then it will contain, if there are any solutions, if there are any factors, it will contain the factors, but maybe it will contain some noise in addition. That would be the third case, and this is what I mean here by inconclusive. Then you don't know if there is a factor or not. And what this means is that your n was not large enough. And then you just repeat the computation with a larger n, and if you have the n large enough, then eventually at some point you will not be in the third case, you will be either in the first or in the second, and then you have solved the problem. And this answers, this settles this case. So this tells us how to do factorization of univariate polynomials over a rational function field. The answer is by linear algebra. And now we can come to this mysterious field, or this mysterious ring. What is this? So let's compare it to the setting here. You know that polynomials are very similar to integers, and that rational functions are very similar to rational numbers. because they are just quotients of integers and they are just quotients of polynomials. And here for the monomials, you know, you have terms, and here you have digits, and that's all very similar. The digit system is very similar to the way how we construct polynomials. But here on the left side, you have something in between. That's the power series over k, and there's no obvious analog on the right hand side. So let's invent something that is between, in a certain sense, between the integers and the rational numbers, in the same sense as the power series are between the polynomials and the rational functions. I'm hesitating to say in between, because you could also say that this one is on this one is here, but okay, so it's in between because it's according to the process in which we are using the things. Okay. Here's a construction. You start with a prime p, and you define this ring, for which there are different notations in the literature. Some just say write set subscript p, but that's the notation that I use for the finite field here. And this is supposed to be something different, so I put brackets around this so that we can distinguish this. This is a new set that I'm now defining what it should contain, and it should contain all the sequences, infinite sequences of integers between 0 and p minus 1. And this is similar like you define power series, because you know that power series are in fact also just the series of the coefficients. And then there's a certain way how arithmetic is defined on power series, and then there's a certain way how we write them as infinite sums, as if they were polynomials of unlimited degree. But in fact, officially, they are just the sequences of their coefficients. And that's the same here. So here we take the sequences, and this is supposed to be this set. And now we want to turn this into a ring by defining arithmetic on this set in the same way as we define arithmetic over the power series ring, but with, of course, with some difference, because otherwise we get the same ring. The difference is that we do the addition with the integers with a carry. So a carry in German is Übertrag. Where if you have an overflow in one of the digits, then you reduce the overflow and put something into the next digit. Okay? So this means that whenever you have a computation where one of the sequences has an entry that is larger than or equal to p, then you keep subtracting a p from the 8th term of the sequence, but then increasing the next term. Like when you do addition and you add two integers, and in a certain digit you get more than 9, well, then you put some digit you keep, but the overflow goes into the next digit. Okay, so I'm claiming that with this modification of the power series arithmetic, you still get a ring. Now, that's not something that you have to believe me, but if you don't believe me, then you have to check it, because I'm not going to show you the proof. The proof is just you have to calculate. As often when you claim something is a ring, you just have to check that all the requirements are satisfied, but here they are satisfied, and I'm not going to show you this here. You can check it yourself. And this is called the ring of p-adic integers. And we write these integers like power series. So that's a bit funny, because it's like the power series notation that we use for power series, except that the variable, the p, plays now the role of the variable. So it's a bit unusual. So before we use this, let's try to get used to it a bit. So here are some examples for the prime p equals 7. If you just have ordinary integers, then this is not so unfamiliar, because then that just means these expansions mean that you're writing the integer in the digit system with the base 7. So this is the result, and yeah, that's a power series where that's a finite power series that stops here, and insofar the integers are similar to the polynomials. So that's not that's not so that agrees with the plan that we had in the beginning to come up with an analog of the power series, and the power series have the feature that they contain the polynomials, and the polynomials correspond to the integers. So this matches. This agrees with what we want. But let's take a negative numbers. For negative numbers, it's already a little bit different because here you get an infinite expansion. So the -2 is equal to 5 plus 6 times 7 plus 6 times 7 squared plus 6 times and so on. And why is this? What this means is that this infinite expansion of this number -2 is a sequence of approximations of -2 modulo higher and higher powers of 7. So I've mentioned a few times in this course already that taking something mod a prime is also some sort of approximation, not in the Euclidean sense with respect to the Euclidean distance, but with respect to the idea that you have some information about the object in the homomorphic image. So if you take the first coefficient, then that's just the usual homomorphic image. 5 is the homomorphic image of -2 mod 7 in the finite field. But now if you take two terms, then I don't know what this is, 42 plus 5 is 47, and 47 is equal to -2, yeah, mod 49, which is 7 squared. And it turns out that you keep going. So if you take an arbitrary finite amount of terms here, up to a certain power of the prime, and then truncate it, then this is an approximation of -2 to a high accuracy, and the high accuracy means that it's equivalent modulo a high power of 7. Okay. Now what about fractions? You can also expand fractions in these p-adic numbers. But how do I get this? So this is a rational number, and I claim that it expands into 6, 3, 5, 4, 3, 5, 4, 3, and so on. And this is true again in the same sense as before. If you take just the 6, then this is the image of this fraction mod 7. But if you take these two numbers and read them as integers, then this integer is equivalent to this rational number mod 7 squared, and these 3 mod 7 cubed, and so on. And you can check that this is true. But checking that this is true is only possible if I give you already the numbers. More interesting question is how do you determine the next number if I don't tell you what the next number is? So the question is, for the next number, what is the value of A8, and it's restricted to 0 up to 6 because P is 7, so that this next approximation is still valid. And the condition is that the rational number should be equivalent mod the next power of 7 to whatever we had before, plus the new term times 7 to the 8, that is still unknown. So if you work this out, then you can move this here to the other side. So I'm trying to solve this equation for A8, which is a bit, looks a bit slippery because I have here things that live where it's not clear where they live. So this is a rational number. This here is an integer, and the equality is supposed to be valid mod this integer. And I want to solve this for this number, and this number is constrained to these integers. Okay, so just solve it. Let's move this to the other side. So this gives this one. And then let's divide by 7 to the 8, which is which means that if you divide this, so I'm using here that this is already a valid approximation mod 7 to the 8. So if I'm taking here the whole equation mod, if I replace the 9 by 8, then this will just disappear and I'll get something that is correct because I assume that this is already okay. So that means if I have here this difference from this and this, then this is something which modulo 7 to the 8 is equal to 0. So if I divide here by the 7 to the 8, then I'm also cancelling the 7 to the 8 from the 7 to the 9, and what remains is just a 7. Okay, but then this is the answer, because then the A8 is just whatever this here is mod 7. So this is something, yeah, mod 7, this is division by 0, but you do the computation here first in the rational numbers, and then you will get an integer, and this integer you take mod 7, and then you get the A8. Okay. Oh, square root of 2 is also funny. If you have, so that's why I first said that it's not, yeah, it's the power series are not really between the polynomials and the rational numbers, because you have also irrational things in it, and that's the same here in the p-adic numbers. You have certain irrational numbers as well, and here's one of them. Square root of 2 can be expanded into a p-adic integer. So what does this mean? This means the same as before. So this means that 3 squared is 9, and 9 is equal to 2 mod 7. And this here is 10. 10 squared is 100, and I hope that 100, yes, it is. 100 is equal to 2 mod 49, and so on. Okay, so how do you get the next term in this series? Let's try the same thing as before. The question is now, what is the next number constrained to 0 up to 6 such that 2 is equal to this approximation squared mod the next power of 7. Now here we have again this approximation is correct, unless I made a typo, but let's assume it's correct. And then the next unknown term is entered with an unknown coefficient, and now I square it. And if I square it, then or if I expand the square, then I will get the square of A8, and that doesn't look very funny, because it might seem that we have to solve a nonlinear equation for the 8, where before we just had to do a linear equation. But it's not so bad, because if you see that when you expand this, then you square not only the A8 but also the 7 to the 8, and the 7 to the 8 squared is 7 to the 16, and this is eaten by the 7 to the 9. So only the linear term of this square survives when you expand it, and that's why we can solve for A8 even though this is a nonlinear equation, and you get a unique solution. So what happens is you expand this, you move the square of this to the other side, which is here, then you divide by 7 to the 8, which also divides the modulus, and you get 7. And here you get 7 to the 8. And here you get only the mixed term of this square, so which is 3 from here, times 8, times A8, which is this, and this is the 2 from the binomial theorem, from expanding the square. And all the other things that are here disappear, because these ones combined with the 7 to the 8 give something that is at least as much as this, and therefore goes away. Okay, so this is again a rational number, and you can compute it in the rationals. Then you get an integer by the assumption that this is a valid approximation, and this integer you can take mod 7, and you get one which is here, and then you have to divide by this, and hopefully this is not 0 mod 7. In this case it isn't, but that's something where we, if you want to generalize, we'll have to worry about whether this can be 0. If this is not 0, you divide by 6 mod 7, and then you get the A8, and this is the next term, and you can keep going forever. In this example, you will always get the 3 here, because the 3 is from the first, and the first is not going to change if you keep going on this side. So here you see, at least for this one, we can be sure that this extends indefinitely. Okay. So square root of 2 is a root of a polynomial, is a root of a quadratic polynomial, x squared minus 2. And what we have just done is we extended here a root of x squared minus 1 in set 7 to a p-adic root of the same polynomial. Now that's what we want to do more generally now. So we assume that we have polynomials over a finite field, and we have a factorization of such a polynomial, and the question is now, can we turn such a factorization into a factorization of a polynomial, of the same polynomial over the p-adic integers? Okay, so let's set this up, and suppose that the f is an integer polynomial, so polynomial with integer coefficients. So I have integers here, and I'm just interpreting them mod prime. And this corresponds to what we saw in the first part of today's lecture, when I talked about with pictures about factorization in a bivariate polynomial ring. This corresponds to the assumption that you have a polynomial that is a polynomial in x over a rational function in t. So actually, if this is integers, then I should here write polynomials in t. But anyway, this is, you see the analogy. And now I'm choosing a prime such that this f is still square free in set P. What is the analogy of this? This is the suitable choice of tau that we made in the first part. Also, I want to choose a P. I didn't say that here. I want to choose the P also so that the degree doesn't drop. That is the other condition for the suitability of tau. Okay, and now I assume that I have a proper factorization of f, but it's a factorization that is only valid mod p. So I assume I have two polynomials, g0 and h0, and I view them as polynomials. So they are polynomials with integer coefficients, but I view them as polynomials that are whose coefficients are in this finite field, and I want them to be coprime. And I can also assume that one of them is monic, because if not, then I move the coefficient to the other one. And yeah, they should multiply out to f. This assumption corresponds to the assumption that we had before, that we can factor in k, because k now is played by the role of k from before is now played by the finite field. And what we want is now an implicit function theorem that works for p-adic numbers instead of power series. So that's what we have to come up with. So let's see how we can do this. It's actually not so hard. A few formulas, but don't be scared. The basic idea is not so complicated. It's very natural. So the assumption is, the basic setting is we go by induction, like before, or like in the proof of the implicit function theorem. So as induction hypothesis, you assume that you have a factorization of f into two polynomials, one of them being monic, so that the factorization is valid modulo not just p, but actually a power of p, the kth power of p. And the task is to turn this factorization into one that is valid modulo the next power of p. So what we want is two polynomials which have integer coefficients and where the degree of hk is less than the degree of h0, so that when I extend each of these two given polynomials by these additional terms with the corresponding power of p, then that will be a valid factorization of f mod the next power of p. So where does this condition come from? Why do I want this degree to be smaller? Because I want to maintain the condition that this is monic. I want to update the hk to this polynomial. So if the hk already has 1 as coefficient of the highest power of x, then I don't want to add something to that highest coefficient. So that's why I make sure that the degree of this polynomial is smaller than the degree of h0, so that the highest coefficient is not affected by this extension. Okay, so that's a normalization that is necessary, otherwise you have a degree of freedom that will disturb your termination condition later. Okay, so let's expand this this product. So we want, this is the same as before, we want f to be equal to this one plus this one times p to the k plus this product times p to the 2k. Now this one goes away because we are thinking mod k plus 1, and this one is something we can put on the other side, and then I will have something on the other side that is valid mod p to the k. I can divide then the whole, okay, so first I've dropped this one here, and then I bring this to the other side here, and now I divide this one is a multiple by assumption, a multiple of p to the k, so I can divide this whole equation by p to the k, and this gives this one, and then I have an equation that is valid mod p, and so this is an explicit polynomial that doesn't have denominators because this cancels by induction hypothesis, and I have to solve this polynomial equation for two unknown polynomials. How would I do this? Let's call this polynomial u, and you know how to do this. This is a task that you know how to solve with your methods from computer algebra 1. That's just a standard application of the Euclidean algorithm. So with the Euclidean algorithm, we can get the cofactors of G0 and H0 because we assumed them to be coprime. Their GCD is 1. So I have I have this S and T in the polynomials of the finite field, but I don't want them to be equal to 1. I want this to be equal to u, but no problem. Just take this equation, multiply it by u. So, and then here's your choice. You take hk as s times u for here, and gk as t times u for here, and then because of the choice of s and t, this will satisfy this equation. It doesn't satisfy yet this degree condition, but we still have a little bit of freedom to adjust this because I can move things away. I can move things back and forth between S and T. So I can take an arbitrary Q from whatever I like, and subtract from here the qth multiple of h0 if I add the qth multiple of g0 to the t, and that's because g0 times h0 is the same as h0 times g0. So this here will be this is a degree of freedom that I still have, and with this degree of freedom I can make this here happen, because I can choose as q the quotient of the division of s times u by the h0, and then this will be the remainder, and the remainder has a lower degree than the h0. And that's it. This is called Hensel lifting. And here's the summary of the algorithm. This is again just a summary with no additional information, just what we discussed. We have a polynomial over the integers of a certain degree n. We have a prime p, and we have an L, and we have an initial factorization. So we have two polynomials over a finite field that are coprime and such that their product is equal to f mod p, and where one of them is monic. And what we want is the lth pair of g and h in this expansion, power series expansion. So we want to get two polynomials, integer polynomials, such that HL is still monic, and the product of these two output polynomials is f mod the next, or mod p to the L plus 1. So first you compute the cofactors with the Euclidean algorithm, and then you instantiate g and h to the given polynomials from here, and then you let k run from 1 to L and do what I explained on the previous slide. You compute the u, and you compute the q, and then you update the h and the g according to these formulas, and you do this k times, and the output is the pair g and h. This is correct because of the reasons that I've already given, and the complexity is also not hard to analyze because you're not doing very much. Here you're doing a GCD computation that takes m of n log n time, and here you're running through a loop of length L. This gives the factor of L in the complexity estimate, and inside of the loop you're not doing anything more than multiplications, so altogether it's just L times multiplication time for the loop and log n times multiplication time for the GCD in the beginning. So here's an example. Let's take this polynomial. It's a cubic polynomial, and it factors mod 7. Here's a factorization, and now what happens if you apply this Hensel lifting theorem is that the shape of the factorization is not going to change, but the coefficients will grow. So this is these are the coefficients mod 7. Here are the coefficients mod 7 squared, mod 7 cubed, mod 7 to the 4, mod 7 to the 5, and so on. How far do I go? Here. Okay. And I will go on forever. There's no limit, and we have seen that any initial factorization can be extended over the finite field, can be extended to a factorization in the p-adic numbers, and that means that here these approximations of this infinite series that makes up the p-adic numbers, yeah, you can refine them as much as you like, and you will never recognize in this way that this polynomial is actually irreducible if you view it as a polynomial over Q. So this is again similar as in the first part of the lecture today, where we had also seen that we can always take a root of a bivariate polynomial, then expand it to arbitrary position with the implicit function field to a root of the bivariate polynomial. Even though the bivariate polynomial may be irreducible if you view it as a univariate polynomial over a rational function field. Okay, so this is completely analogous here. But then let's conclude this. This is Hensel lifting, and let's now turn to rational numbers as coefficient fields. So this is the third part for today. After this one and this one, we now ask, how do we do this factorization over Q? Okay, so let's see. What's the problem? Factorization over Q means you have given an f with rational coefficients, and we want to apply the same idea. We factor it modulo p. Okay, but then the problem is that by going mod p over the finite field, it may break into smaller factors. So what I mean here is, if you take this polynomial and its factorization over the rationals is this, so that's what we want to determine somehow, but let's assume we know this already. But if you take this modulo prime, for example 23, then you see this breaks into further factors. And these further factors somehow correspond to the other factors. So these two factors, mod 23, correspond to this factor, and the other ones to the other one. But you don't know this. So if you go mod 23, You get this factorization. Then the question is, given this, how can we find this? One initial idea that you may have is to use Chinese remaindering. So that's a good idea. Take several primes and consider several factorizations. But that doesn't really help here, because then you get several factorizations, and we have seen in the beginning when we talked about how polynomials factor over different fields, that you might not even get 4 factors for every prime. The factors may break in a different shape, but even if they break into 4 factors, then you don't know which of these 4 factors belong to which of the 4 factors modulo the other prime, and there may not even be a correspondence because it just breaks differently into 4 factors. So that's why Chinese remaindering is not the right approach here. You have to do something different. And yeah, the idea is to do Hensel lifting. So we can take this factorization here and expand it if necessary to a factorization modulo higher powers of 23. And this will be useful if the factors here will have will have longer coefficients. And of course here I will also need longer coefficients, because somewhere the information has to come from. Well, let's suppose we are in a situation where the 23 is already enough for enough accuracy for the factors, and then the problem remains: how can I recognize that these 2 factors go together but not these 2? And one approach is you just try out all possibilities. So here's how to do this. It's not going to be an efficient algorithm, but it's an algorithm. That f is a polynomial that we want to factor, and we suppose that we are given the factors of it mod prime, and then some subset of these g's will form a factor in f. Okay, maybe that's the subset here. These indices here form a subset. And how do you recognize this? Yeah, the one thing you can do is you can just compute this product here of this subset and multiply it with the leading coefficient of the integers, and you get a polynomial mod p. And you interpret this polynomial as a polynomial over the integers. There you would take then reconstruction from the finite field into the integers, where you adjust the sign, so the finite field elements are interpreted as elements, as integers that are in between minus p half and plus p half, so that you recognize a negative coefficient. And then you have a candidate polynomial that has integers as coefficient, and then you just check whether this polynomial divides f over the integers, and if it does, then you are happy. So I already said how to translate these coefficients from set p to set, and yeah, and yes, and the question is, can we just map them to equivalent integers with smallest degree? Yes, that's possible, but in order for this to work, you have to make sure that the p is large enough, and large enough means it should be larger. The p should be larger, should be at least twice as large as the coefficients that appear in the real g. So we are assuming here that this is a valid choice that corresponds to a factor, a proper factor of f, but we want to recognize this. So if we do here a calculation mod p, then maybe if the p is too small, we will throw away a little bit of information, and then this divisibility will not hold anymore in Q, and then we will not observe that this is a factor. In order to avoid this, the p has to be large enough. And what means large enough? Large enough means it should be at least twice as long as the largest coefficient in G. Unfortunately, we don't know what the largest coefficient in G is, because we know only f. F is part of the input and G is part of the output. G is a proper factor. We want to find the G. So, um, well, we need a theorem that tells us how big the factors can be, and this is the theorem. It's also a theorem that maybe you have seen in Computer Algebra 1 already when you talked about GCD computations in bivariate polynomial rings, or maybe some other context. But anyway, so here's the theorem. You take a polynomial and you define a norm of the polynomial, the infinity norm, which is defined as the largest coefficient, and the 2 norm, which is just the Euclidean norm of the coefficients. And then there's a theorem that says if you have two polynomials, f and g, where one divides the other, and n is the degree of the larger polynomial f, then there's a bound on how big the coefficients of the factors can be in terms of the coefficients of f. So this is the main statement of the theorem, this inequality. This one is easy, and this one is also easy. And this is something that I don't want to prove here. Let's just take this for granted. It's not horribly difficult to prove this, but it would take an hour or so, and it would need, because it needs some tools that we haven't discussed, and that I would have first to introduce. So it's not a big deal to prove it, but I don't want to show it. And if you want to see it, you can find a proof in the book of von Sogarten and Gerhardt. I want to point out, however, that this theorem illustrates again that integers are more complicated than polynomials, because in the polynomials the question doesn't arise. If you have a divisor of f, then it's clear that the divisor has at least as high a degree as f. And we actually used this already in the first part of the lecture when we talked about bivariate polynomials. And that's not the case for integers, or for polynomials over the integers. And in fact, that's not just a weakness of the theorem, but it's in fact a feature of the polynomials. Here's an example. If you look at this polynomial, x to the n minus 1, it has extremely small coefficients, just 1 and minus 1, and 0, so it can't be much smaller than that, the norm of a polynomial. But if you let n go to infinity, then these polynomials will have factors. You will observe factors of the polynomial whose infinity norm can grow arbitrarily large. So here this 2 to the n is not just a weakness of this estimate, but it's really a necessary concession that you have to make for the existence of possible factors. Okay, good. So once you have this, then you can put the things together and obtain the factor combination algorithm that factors polynomials with integer coefficients, but it doesn't factor them as elements of here, but it factors them over the rationals. That's an important detail, because otherwise you would have to factor also the leading coefficient, and that would be an integer factorization, which we don't know how to do. So we assume we are given a polynomial with integer coefficients, but we understand it as a polynomial over the rationals. N is the degree, and the output is either an irreducible factor of f, or we return f itself if it's irreducible. Okay, so here's how it works. You either you choose a modulus, which is either a prime or a prime power that is sufficiently large, and sufficiently large is clarified by Mignot's bound, and that's one condition on the prime power. And then this is okay, and this is a typo. This should be a Q. And a second condition on the prime power is that the square freeness should not be disturbed. So remember, that's a condition that we needed in order to be able to get an initial factorization. So here we compute factorization over set Q. So set Q Q is a prime power, so either it's a prime, then you use Cantor-Zassenhaus, or it's a prime power, and then you use Cantor-Zassenhaus followed by Hensel lifting. And in either case, after step 2, you have a factorization of f that is valid mod Q, and Q is a large prime or a large prime power. And then you go through all subsets of these G's. You start with the small subsets and then you increase until m half, because if you go further, then you will just see the complements of subsets that you have already investigated, and that's not necessary. So for every size of subsets, you go through all the subsets of that size and check candidate factor G that is obtained by the leading coefficient of f and the product of all the elements of the subset that you have chosen. You take it mod Q and interpret it as integer with coefficients, as integer polynomial with coefficients between minus Q half and Q half. And as such, you divide it, you do a trial division of f by G and see if the remainder is 0. If so, you have found a factor, and if you haven't found a factor in the entire loop, then that's a proof that f is irreducible, so you return f according to the specification that the output value f indicates its irreducibility. So that settles the factorization over Q. You can do a factor combination. But that's not the end of the story, because a factor combination will take as long as how many subsets there are, and there are many subsets, and so we have an exponential runtime. That's not acceptable. We have to work a bit more in order to get an algorithm that has polynomial runtime. And in order to get such an algorithm, recall what we did when we came from Laurent series to rational functions. We didn't do factor combination there. We could have done factor combination there as well. We could have said, okay, I compute all the power series roots, and then these correspond to x minus the root as the factors of the polynomials m that we had there, and the factors here would have to be combinations of these roots. So I take some set of roots and multiply the corresponding polynomials x minus power series together, and see whether such a combination gives me a factor in this polynomial ring. And we didn't do this. It would have worked, but what we did was to choose one root and find an other polynomial that has the same root. And that's maybe something that we can do here as well. So let's see how we would do this. Okay, so let's suppose you have f and u, integer polynomials, and suppose that u is an irreducible factor of f mod p. Okay, so this is one of the g's. And what I want now is, instead of combining this u with other irreducible factors to a candidate factor, I want to construct a multiple of u, but not too high a degree, but with a degree that's less than f. I remember, like we did it with the linear algebra approach in the first part of the lecture, such that the GCD of f and g is non-zero, is not 1 in the polynomial ring, and that would give me a factor of f. Okay, okay, so we make an ansatz. We say, what could the g possibly look like in order to be a polynomial, a multiple of u? It will be u times something with undetermined coefficients up to a certain degree, and the degree here is degree f minus degree u minus 1. So the D is clear what it would be because I have the F and the U. What I don't have is the coefficients. That's what I want to determine. So what we need in order to determine reasonable candidates for these C's that are worth checking, whether this G has a GCD with F, we need some constraints on the C's. So where could they come from? Here's the theorem. The theorem says if you have F and G and U, the polynomials, but non-trivial polynomials, all of them, including the U, n and m, the degrees of f and g, and you suppose that the q is larger than something, this one, and you also suppose that u divides f and u divides g when you view them as polynomials with coefficients mod q. Then the theorem says the GCD of f and g will not be 1 in Q. No, okay, so I didn't expect I would get that far. Let me see if we can prove this. Proof. So here we go. So we want to show that GCD of f and g is not 1, and the GCD is non-trivial if and only if the resultant is non-zero. So we prove that the resultant of f and g is 0. And so where would that be? So these are polynomials in set x, and the equality is supposed to hold there. So because this is where we want this to happen, the GCD should not be 1 when a few f and g as polynomials over the rationals. Doesn't matter here, rationals or integers, but not mod something. And so what can we say about the resultant? Remember what the resultant was. The resultant was the determinant of the Sylvester matrix. And so the determinant of the Sylvester matrix was defined like this. F0, F0, Fn, Fn. So, and G0, G0, Gm, Gm, with n rows here and m rows here. Now there is a theorem of Hadamard that says that that gives you a bound on this determinants. So this here is bound by Hadamard by norm f, 2 norm of f from this vector. Now the second vector has the same norm, and the third and so on also. So this is getting a power of m from these m columns times g from here, the 2 norm of g to the power of n. Now, so this is the Hadamard bound for the size of the determinant, and the assumption is that q is bigger than this. So this is still less than q. But we also know we know that u divides f and u divides g mod q. So if I'm doing the GCD of f and g when I view them as polynomials over a ring mod q, then the GCD at least contains u, and u has a positive degree, so the GCD is not 1, and therefore the resultant of f and g, which is an integer, also here it's an integer, this resultant will not be, this will be equal to 0 mod q. But if you combine those, this here, the resultant is less than q, but it's also 0 mod q, then those two together would give that the resultant of f and g is equal to 0 in the integers. And this is what we wanted to show. Okay. So what does this help you? Now we can use LLL. We can use LLL to do what we did in the beginning with linear algebra. And what we will do is we will ask LLL to get the coefficients of this G, and the G, remember the G here is a linear combination of u times x to the something. So the coefficient vectors of the coefficient vector of u is this one, and then the coefficient vector of x to the something times q is the same, just shifted a little bit like in the Sylvester matrix until here. But then also you have to tell LLL that everything is taking place mod q. So you add these vectors here, and then you get a lattice, and this lattice will contain necessarily the coefficient vector of every such g. Every g that is written in this form. What we want is a g that has a common factor with the f, and we can ensure that this appears if we make the q large enough because of this choice. So this is what we will do. G, so a vector of integers belongs to this lattice, the way we constructed it, if and only if u divides this polynomial here mod q. And with LLL we will find a short vector, that means a vector where these coefficients are small. Okay, so how small should they be? Let's recall what LLL can provide. First, we know how long the coefficients of a factor can possibly be. We know this from Mignot. And then we know that LLL can find a short vector that is at most this times longer than the shortest. And so if there is a factor of a certain degree m, then using LLL we can find in this lattice a polynomial g which is at most this long. So if there is a factor, then there is the corresponding so then call this factor m. It will have at most this length. So LLL must find a vector that is at most so long, because we know that the g is a vector in the L. Okay, now we have to ensure that LLL doesn't just find some short vector, but we want to find we want to be sure that a short vector corresponds to a factor. And we can regulate this by making the q large enough. So we ensure that the q is larger than this, and for this we need this estimate, because we don't know the g, but we have this bound on g. So here is something, a quantity that depends only on things that we know, the size of f and its degree. So this is how we have to choose the q. And then we get this factorization algorithm that is based on LLL. So it takes a square-free polynomial as input, and it has degree n, and it returns either a proper factor of f or again f itself if f is irreducible. So you start by choosing a sufficiently large prime, and this is the formula that says it's sufficiently large. Then you compute an irreducible factor of f mod q. If there is none, because f is already irreducible mod q, and then you are done anyway. But if u is smaller in degree than f, then you cannot be sure that u itself is also a factor of f over the integers or over the rationals. So in general, you would have to take a multiple, and we now use LLL to construct this multiple. So we try multiples of increasing degrees, starting with the degree of u. So d is the degree of u, all the way up to n minus 1. N is the degree of f. So you get that the candidate that you will choose will be the smallest vector in the LLL basis, in the reduced basis of the lattice that I showed on the previous slide. You take this g, translate it as a polynomial, compute the GCD of g and f in Q, and if this has positive degree, then you have found a factor. And if you never find in this way a non-trivial GCD, then this proves that the f is irreducible. Okay, so here's let's just finish this. It's just a few more minutes. Here's the summary of the algorithm. The complexity is polynomial time. So we have eliminated the exponential complexity that we got from the factor combination. It's polynomial time here. You get this just by taking the result or the complexity result about LLL and checking how big the sizes of these quantities here are, and then you get this this result. But again, this is just operations in integers, so it's not a meaningful result. If you state it like this, you have to, if you talk about integers, you have to look at the bit complexity. It can also be worked out. It's a complicated expression. The details are not so important. The important thing is that it's really polynomial time. So you can factor polynomials in polynomial time. And this is now an algorithm that just finds some factor, and if you want to have a complete factorization into irreducibles, then you would apply it recursively, and it wouldn't take altogether much longer because things get smaller during the recursion, and it's dominated by the computation at the top level. Unfortunately, this algorithm, even though it's faster than the factor combination in theory, in practice it's often slower than factor combination. And so this means that the story is still not over. Factorization in QX, we can do it with LLL, but somehow that's just really a theoretical result. And next time I will show you another way how to use LLL for factorization, which is fast both in theory and in practice. And then that would be the algorithm of choice and the current state of the art for factorization, for factoring polynomials over the rationals. So for today it's enough. Thanks for listening and sorry for going over time. See you next time.